Welcome to this tutorial on Simulink best practices for large and complex models. In this session, we'll take a look at how data can be managed in Simulink. Effective data management in Simulink requires selecting the appropriate workspace for variables, parameters, signals, buses, and configurations. The MATLAB base workspace, accessible to all models, is convenient for quick prototyping but not well suited for large or modular projects. The model workspace keeps data local to each model, ensuring encapsulation and reusability. Mask workspaces store parameters within masked subsystems, enabling clean, reusable block interfaces while hiding implementation details. For larger projects and team-based development, data dictionaries provide a centralized, external repository that separates design data from the model itself, making it easier to maintain, share, and version control parameters and signal definitions. They support features like linking to reference dictionaries for sharing common data across projects, managing multiple design data sources consistently, and integrating seamlessly with tools such as requirements traceability, code generation, and configuration management systems. This table summarizes the features of the base workspace, model workspace, mask workspace, and data dictionary. Feel free to take a moment to look it over. Let's explore a few use cases of data hierarchies. In this example, each Simulink model is linked to its own data dictionary to manage model-specific data independently. These model-specific dictionaries can then reference a shared data dictionary that contains common data used across multiple models or projects. This hierarchy enables centralized management of shared parameters and signals, promotes consistency, and simplifies collaboration by maintaining common data in one place while allowing models to keep their unique data locally. In Simulink Model Explorer, you can click View Hierarchy to open the Dependency Analyzer, which provides a visual representation of the architecture and relationships among reference data dictionaries. This tool helps you easily navigate through the hierarchy, understand dependencies, and manage shared and model-specific data more effectively within your project. This example demonstrates how the Dependency Analyzer helps visualize the hierarchy of reference data dictionaries. In addition to this hierarchy, projects often include a top-level model that integrates and references multiple component models. The data associated with this top-level model can be managed in different ways depending on project needs. It may be stored in a centralized data dictionary to ensure consistency and support version control across the entire project, or alternatively, for simpler use cases or rapid prototyping, it can be kept in the base workspace, which provides quick access but less encapsulation. A slight variation of this use case occurs when one domain-specific data dictionary references another, allowing projects to separate data by domain, such as powertrain or chassis, while still sharing common parameters, signals, or configuration settings across multiple models. Another use case is to store data in the mask workspace instead of using a data dictionary. The mask workspace is local to the masked subsystem and is often used to encapsulate parameters specific to that subsystem, ensuring that the block remains self-contained and reusable. This approach is particularly useful when designing custom blocks or libraries, as it provides a clean interface for users while hiding internal implementation details. Another alternative for loading data into the mask workspace is to call a MATLAB script from the mask initialization callback, where the required variables are defined and assigned. This method allows designers to keep parameter definitions organized in separate script files, making them easier to edit, reuse, and maintain, while still ensuring that the variables are automatically loaded into the mask workspace whenever the model is compiled or the block is initialized. A final use case I'd like to highlight is that a domain-specific model that uses libraries relying on the mask workspace to store data. The domain-specific model itself can store its data in the base workspace, model workspace, or a data dictionary. To conclude, in Simulink modeling, there is no single right or wrong architecture. What works best often depends on how teams collaborate, share models, and manage data. However, establishing a top-down design early in the development process can provide clarity, improve modularity, and support better collaboration across teams. Okay, let's go over configuration settings in Simulink. Every model has a configuration set that defines things like solvers, diagnostics, and code generation options. For simple cases, using the embedded configuration set is fine. But in larger projects, it's better to use referenced configuration sets. These let multiple models share the same settings, improving consistency and making maintenance easier. You can store these in a data dictionary or a MAT file. It's a good idea to set this up early in the project to support team collaboration and reduce errors down the line. Alright, I hope this session gave you some useful insights into managing data more effectively in Simulink. In the next session, we'll shift our focus to project management and team collaboration in Simulink. I look forward to your participation.